In this video, we're going to talk about homogeneous linear equations with constant coefficients. Let's go ahead and just look at several examples here, and I'll try and make sure we get examples from each case. Won't do a ton of problems here because I think that this is going to become pretty straightforward after you see each case. So when we see something that is like this, 4y double prime plus y prime equals 0, we're going to make an auxiliary equation out of this where we replace the derivatives of a particular order with a variable raised to that power. So I'm going to use the variable m here. That's the way that I learned it. So 4m squared plus m equals 0 is going to be my auxiliary equation here. Then I'm going to factor this and solve it for m. So m equals 0, or 4m plus 1 equals 0, 4m equals -1, and m equals -1/4. When I have distinct solutions like this, I'll call this one m1 and this one m2, then I have a solution that looks like c1 e to the m1x plus c2 e to the m2x, so on until I run out of distinct solutions. We'll have another case coming up here in a little bit where I have repeated solutions, and these are both real solutions, so distinct real solutions, repeated real solutions. And then the third case is going to be if I have a complex solution, and we can have an extension of case 2 for case 3 with what happens if we have repeated complex solutions. So that will pop up in one of the examples that I'm going to do here in a little bit. But this is the simplest form, is where I have distinct real solutions here. So my y is going to be equal to c1 e to the 0x plus c2 e to the negative x over 4. Well, e to the 0x is e to the 0. That's just 1. So this is the same thing as c1 plus c2 e to the negative x over 4. Let's look at the next question here. Y double prime minus y prime minus 6y equals 0. So this is going to make an auxiliary equation that looks like this. Notice this is the 0th derivative, so m to the 0 power is 1 there. I'm going to factor this if possible. Minus 3 plus 2, and this is going to be m minus 3 equals 0, or m plus 2 equals 0, m equals 3, or m equals -2. So I get y equals c1 e to the 3x plus c2 e to the -2x. We have y double prime plus 8y prime plus 16y equals 0. This is going to be an example of case 2, m squared plus 8m plus 16 equals 0. Breaks down into m plus 4 quantity squared equals 0. So I have m plus 4 equals 0. I have a multiplicity of 2 for this answer. M equals -4 multiplicity 2. So that's going to look like y equals c1 e to the mx plus c2x e to the mx. And I keep going with powers of x here. to differentiate each term until I'm 1 degree less on x than my multiplicity, so that I have all of these solutions accounted for. So the first solution is just c1 e to the mx. The second solution, c2x e to the mx. The third solution would be c3x squared e to the mx if I had a multiplicity 3, and so on. So let's go ahead and write the answer here, that this would be c1 e to the negative 4x plus c2x e to the negative 4x. Next one here, 12y double prime minus 5y prime minus 2y equals 0. And we're going to factor. And so let's think of factors of 12 that let's see, so 3 and 4. And then this is going to be negative 2. So I want negative 2 and positive 1. Give me a, nope, that's not right, a negative 8. So, and a positive 3 will give me a negative 5 there. So this is 3, should have written my auxiliary equation here and didn't do so. Sorry that I skipped a step for you. So this is 12m squared minus 5m minus 2 equals 0. That's what I'm factoring. So 3m minus 2 equals 0, or 4m plus 1 equals 0. 3m equals 2, and m is equal to 2/3, or 4m is equal to negative 1, and m is equal to negative 1/4. So that gives me y is equal to c1 e to the 2x over 3 plus c2 e to the negative x over 4. All right, I think that's probably enough case 1 and case 2 for right now. Let's do a couple from case 3. So moving on here, y double prime plus 9y equals 0 makes m squared plus 9 equals 0. So m squared equals negative 9, and m is equal to plus or minus 3i. I'm going to put a 0 there to be explicit, because this, to me, I'm going to think of it as alpha plus or minus beta I, where my alpha in this case is 0, and my beta in this case is 3. Now I want to write my solution in the form of y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. That's what case 3 tells me to do when I get a complex solution like this. So y equals e to the 0x, 0 c1 cosine of 3x plus c2 sine of 3x, and that e to the 0 power is a 1 that I don't need, so y equals c1 cosine of 3x plus C2 sine of 3x. Moving along, got y double prime minus 4y prime plus 5y equals 0. So this becomes m squared minus 4m plus 5 equals 0. If you want to think about that for a little bit, there are no factors of 5 that add up to be -4. So I'm going to complete the square here. Half of the middle number squared is going to give me a +4. And that gives me m minus 2 quantity squared is equal to a -1. M minus 2 is equal to plus or minus I. And m is equal to 2 plus or minus I, where my alpha is equal to 2 and my beta is equal to 1. So that makes y equal to e to the 2x times c1 cosine of x plus c2 sine of x. Let's see, that was that one. Let's do one more just so that you see that the answers don't always have to come out to be so nice and neat. So 3y double prime plus 2y prime plus y equals 0. So we have 3m squared plus 2m plus 1 equals 0. And I'm not going to be able to take factors of 3 that add up to be 2. That's not going to happen. So let's go ahead and start making this look like this. Squared plus 2m equals -1. Then m squared plus 2/3 m is equal to a -1/3. Half of the middle number squared is going to be a 9th. So this is m plus 1/3 squared is equal to -2/9. And then m plus 1/3 is equal to plus or minus √2/3i. So m is equal to -1/3 plus or minus √2/3i. And y is equal to e to the -1/3 x, that's -x/3 times cosine of √2/3x, the c1 in front of it, plus c2 sine of √2/3x. Close that bracket up. And you can do some more examples. There's some initial value problems and some other things where they switch the variables up, and you need to be careful that if it says dy dt, that you make t your independent variable here. If it says du dr, then make this u equals and use r's over here, things like that. So just pay attention to your variables as you work these problems, and make sure that your dependent variable is on this side all by itself and that your independent variable is here. If you have a differential that's written there to let you know what your independent and dependent variables are. All right. If you are given initial conditions, then go ahead and solve for your C1 and C2 using those. but really the process isn't any different. It just gets longer from there if you're given some initial conditions. So that'll be it for this video. That showed you some of case 1, case 2, and case 3. And we'll come back, and next time we'll deal with the idea of undetermined coefficients and the superposition principle for dealing with non-homogeneous linear differential equations. So up to this point, we've had everything equal to 0 on the right-hand side. Next time, we'll start talking about how to come up with a guess of what type of particular solution would work to make this not equal to 0. And we'll use the method of undetermined coefficients will be the first way that we will be looking at that. We'll use some other approaches later on in the chapter. All right, see you for the next video.